We see projectile motion in our lives every day, from kicking or shooting a ball in the air to a cannonball being fired. Projectile motion is always visible to us. For our media project, we decided to test which angle of 4 angles, 15, 45, 65, and 90 degrees, would travel the farthest using a Nerf gun and its bullets. We did this by having one person hold their arm out vertically at a 90-degree angle and measure the height from their hand to the floor. For the horizontal angles, one person positioned the Nerf gun using a backboard that had the angles drawn on them using a protractor. Then they shot the Nerf gun in the air and measured the distance it traveled by using a tape measure from where the bullet was shot to where it landed. This procedure was repeated 3 times for each angle. Our prediction before conducting the experiment was that the 45-degree angle would travel the farthest because it splits the upward and forward forces in half. For our data, we found the time by using this equation. From this equation, we found that the time of flight depends on the gravity acting on the projectile and the height that it reached. The distance that the projectile would travel is fixed by the condition that y = 0. This means that it is determined by the velocity, the gravity acting on the projectile, and the angle that it was fired at. Thus, the equation shown was used to calculate distance and range. The analysis done via vernier included tracking the Nerf bullets from where they shot out of the Nerf gun to when they hit the ground. The initial velocities of each angle were then determined by using video analysis by aligning the axes of the origin to the initial shooting direction of the Nerf gun. These initial velocities were then utilized in finding the predicted distances. Our prediction that the 45-degree angle would go the farthest was proven when we compared the results of the predicted and observed distances. The average observed distance of the 45-degree angle covered about 10.7 meters, while the other angles covered less. The predicted distance for the 45-degree angle was 11.6 meters, which showed a 7.76% error when using the percent error equation. Compared to the other angles, the 45-degree angle did indeed cover the most distance, while the 90-degree angle covered the least, which proved our prediction. The 45-degree angle went the farthest because it provided both a long time for the bullet to be in the air and constant horizontal speed. When the angle is steep, the vertical component of its velocity becomes greater, which means that it will spend more time in the air. However, this also means that the horizontal component of its velocity is small, which leads to the bullet not covering much distance. This was shown when we fired the Nerf gun at 65 and 90-degree angles. When an angle is smaller than 45 degrees, the horizontal component of its velocity is larger, but the bullet spent less time in the air because it started closer to the ground. This was shown when we fired the Nerf gun at 15 degrees. We have to also point out that there may have been some errors during our data collection, since the Nerf gun may have not been perfectly level while firing. Air resistance might have also affected how far the Nerf bullet has traveled.